Okay, I'm gonna go outside my comfort zone here and try a new technology that all the people at work are using now. Now, this is also a little bit of a knowledge check because, well, we've done this lecture before. Depending on your level and interest, it is a deep dive, a shallow dive. So a couple of quick things here first, just to loosen everybody up, because the rest of this is a monologue. So if you haven't used Menti before, has anybody not used Menti before? Okay, you basically go to that website, menti.com, they'll ask you for a code, you put that code in. And you can answer like up to 3, I think I had it set to, and it's just gonna, this is my first ever. It'll just make a little word cloud here. All right, here. That's it, that's all anybody thinks. All right, good answers so far. Dark target, all right. Okay, cool. So you know what atmospheric correction is. So let's go to the next one. Oh, not that one, that's the last. That's okay, yeah. So this is one of the things we're going to spend some time talking about today, because it's terrifying how many other sources of information you need to do this right. If only we had aerosols as an ancillary data source. Pressure, yeah. Yeah, so a couple of these things we're going to solve for. It's not yet. Wind speed's a good one. Pressure. A lot of pressure, front angle. Yeah. Okay, here's the trick question. Why would I use field data? Atmospheric correction. The data you're collecting that goes into algorithms that somehow go into this correction. Let me ask the question another way. What ocean color or biogeochemical data that you collected 2 days ago would potentially influence atmospheric correction of it? Okay. No pressure. We know where we're at. Okay, so these are the things we're going to talk about today. Let me get out of this. All right. Good. There are no shortage of 3.5 million moving parts in an atmospheric correction scheme. We're going to do a really, really high bird's eye view of what these things are. There are going to be a lot of equations. We're not going to stare at them. We're just going to use the equations honestly as like a roadmap for talking points. Most of this presentation is for your reference later. Like there's a lot of material and a lot of words and places that are there intentionally in case you want to look back on it. But good God, just sit back, relax, ask questions, but just let it kind of flow over you because there's a ton of things that go on. And frankly, I'm trying to evolve this into something that is a little bit agency or sensor independent because there are so many emerging schemes to do certain things differently, which is great. But there are fundamental problems that have to get solved. So I'm going to give you an example of how NASA solved them in the past, not necessarily how it's going to be solved in the future or how other agencies do it, but they're all common problems. These are great references If you want to take a deeper dive and actually think about it, we have an atmospheric correction technical memo that's easily found online. And it's a complete section in the Oceanoptics web book as well, too.
And the project is very interesting because it started with Kurt really wanting to understand how NASA makes things.
Yeah.
And finding out that it's really, really difficult to get all the details about how the stuff is made. And in discussion with NASA, in the end, they said, you know what, we would like to know how it's
Yeah, that's good.
and that's how the technical.
Yeah, exactly. It was born out of like 2013 class or something like that. Because I created this for my own. I was like, oh, when we were talking about it, let's walk through atmospheric correction. Then I realized, even having been there for many years, I didn't know how all the parts moved. All right, so we're going to do this is why I asked the questions I did. Mechanical steps, that'll be cool. There are a lot of places where you need ancillary data. In this case, we're talking about things like ozone concentrations or sea surface temperature for certain parts, things that a single instrument typically doesn't measure by itself. Like CWIS, motospheres, pace, whatever, they don't measure surface pressure, but you need surface pressure for something. Where does that information come from? And then there is a lot of in situ data that goes into this. And those are some of the assumptions that need to be made kind of towards the end of the process that we'll talk about. But field data, like what you are collected, actually does feed into this as well. And that's not well known. So you've seen things like this before. This is just the gentle entrance into this. Passive remote sensing here, downwelling irradiance. You have happy little photons. They interact with the sea surface. Anytime a photon interacts with anything, two choices: absorbed and scattered, water leaving reflectance. Note that the satellites really just operate like your eyes do. All they're doing is measuring different colors of the rainbow, but they're doing it in a very systematic way. And what we're really talking about is this process. Like, how do we get from what's sitting at the top of the atmosphere, remove the atmosphere so that we get the water leaving signal? And all we have to work with is measurements of light intensity over some spectral range from the satellite. It's all the information that that instrument is collecting. Okay, so we measure top of atmosphere radiances. This is going to be the first slog through an equation, but it has a purpose. This is probably the simplest explanation of it. And right now, everything we're defining up here, L is radiance, is me defining it at the top of the atmosphere. So you have Rayleigh scattering, so air molecules. You have aerosols. You have how aerosols interact with molecules of air. Do you know what I mean by aerosols? So let's start with that. Think of them as particles in the atmosphere, just like hydrosols in the ocean. So this could be sea salt. It can be Saharan dust. It could be brown or black carbon from an urban area. It's just all of those other things that are in the atmosphere that are above and beyond aeromolecules themselves. There are contributions by sun wind, contributions by background sky radiances. That's just how, photons are getting scattered around and making the sky blue. You have foam and white caps, and then you have the signal that you actually care about, which is what's exiting the water column. And it's just kind of graphically illustrated here. The reason that this is hard is that if you sum up everything that the atmosphere contributes, it's this orangish line. The fraction of this is huge. It's 80 to 90%. The water leaving signal is this green line. That's our target. The sum of all of this is what we measure, and we're trying to remove 80 to 90% of the signal. Now, an atmospheric scientist would turn around and be like, nah, the water is noise. The atmosphere is interesting. But we don't have that luxury. We got their signal is our noise. So, you've done your radiative transfer lab, you've done your hydrolyte lab. We've talked about the fact that in a forward model, you can push this and photons to the system and come up with really credible exact answers. Problem we have, like we were talking about on my first day here, is that in a perfect world, you would do all of that and you do perfect calculations, but you can't. It's too computationally intensive. And so this is, the order of magnitude estimate. And why agencies have to take shortcuts or use lookup tables or do preconceived calculations, because you just can't do this. So we say this is the global area of our ocean. We have a singular instrument gets global coverage, so it sees all of that in 2 days or so, and it's collecting this much data, something on the order of 11 megabytes per second. You can scale to the pixel size, blah 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 blah. The point is that this is the number of pixels for one instrument we would have to process every 2 days. So we're in the hundreds of millions. Now we have all of these other instruments to do with this. And then you have a community that basically says, I would love to have this data in my hand within 3 hours or less of acquisition. And so you're crunching an amazing amount of data. So you can't do these full-blown amazing calculations. And you definitely couldn't do this 40 years ago. And so there's a lot of steps in this process that allow for the inputs. So you want the atmospheric correction to be as accurate as possible, but they have to be computationally fast. And just file that way in the back of your mind, because the world is changing, and you can do other things that maybe improve this process. Okay, so for convenience, we start moving towards the sea surface. So this is how you might express this additive equation at the top of the atmosphere. Now, if we bring it down to the sea surface, well, we're not accounting for L sky anymore, but you need to take your surface measurements and then bring them. You acknowledge that you have to bring them to the top of the atmosphere. So we add a couple of transmission functions here too, and we'll talk about those. So don't worry about it too much. But you want to know that there's 2 forms of this. There's the direct one, and then there's the diffused one. And that's really just whether or not the path connects the source and observer, or if everything's getting scattered into other directions. So that's the diffuse. And again, stop if you want to go into any detail here, but otherwise, I'm going to try to keep this, kind of at a high light level. No pun intended. Okay. So for computational efficiency, we do some factoring here too. And the only reason that we do this is computational efficiency. If you're the Kurt Mobley of the world, you don't want to use this equation. You want to use these and push all your photons to the system. If you're NASA or ESA or JAXA, you have to use something like this. Again, not really a devil in the detail that you care about, but as you encounter papers and things, you're going to see the expression written different ways. And I just wanted to give you a very, very quick rationale for why you might see something written like this. So this is a lot more, convoluted and harder to understand than, say, what you might be more familiar with, especially since, we're dividing absorptions and backscattering into linear things like that as well. This is one of those slides we're not going to talk about and we're not going to read right now. It is simply stating that given everything you saw in the previous slide, we pre-compute and store in lookup tables some of these values. So Rayleigh scattering, for example, can be a semi-exact calculation. And so instead of having to calculate it for every single pixel, we pre-compute, we spend a lot of time, let a bunch of radiative transfer happen in the background, and what pops out the other end are lookup tables. And it's far easier just to navigate a lookup table than do the calculation in real time. And we do that for a couple of different things, like polarization sensitivity, diffuse transmissions, and so forth. Okay, so this is going to be the roadmap. The way we're going to handle this lecture is really just go piece by piece, and I'll just talk about what each of these terms means and how we calculate them, so that you get the general idea of all of the crazy steps that go into all of this. We want a water leaving reflectance, remote sensing reflectance. All of our algorithms basically tune to this, but this is what we're measuring, and all of these other variables are in our way. So, any questions so far? So it's an okay level. If you want to go into the details, I'll try. If this is too much detail, we can even just back it up.
What is just generally what is How would you characterize the procedures?
We'll go through each one of those. Yeah. And honestly, this is simultaneously intended to be scary, but not scary. Like not scary in the sense you might understand the guts of it, scary in the sense of all the sources of information you need to actually do this.
And each one with its own answer.
Yeah, we're gonna have a poll on that afterwards. Okay, so this is pretty much what I just said. We measure this, we desire those. Okay, so in this case, anything that you see in the blue circle here is something that we basically pre-calculate or can model. This is the one that's really not known. What is the aerosol? What is the interaction between aerosols and air molecules and radially scattering? So this will be the last thing we get to. What we'll do for the next few minutes is just kind of crunch through this so you get a sense of what's going on. And then we'll slow it down and figure out what we're going to do to solve that problem. And again, this is a lot. So if you're not writing things down, I don't care. Love it if you didn't put your head on your desk, but I get it if you do. All right, so top of atmosphere radiance, we've already pretty much covered this. This was a modeling exercise that appears in an IFCCG report. It's basically restating something that I already said, that the fraction of top of air radiance is very, very small when you're only considering the sea surface. So the curves here, which are wavelength versus top of atmosphere reflectance of different kinds of water. So you can see that there's different spectral shapes that you might get there, for particular atmospheric conditions. And then this shows you the fraction that is coming from the water. So in some cases with sediment dominated, maybe you might be able to tease out some information. But if you're just looking at open ocean or you're looking at really, really, really black water like that's out there, your goal is to somehow tease out 10% of the 10% of what your instrument is actually measuring. Again, stated another way. So the way I put this together in terms of kind of understanding the contribution of all the parts is really just to have what effectively is going to be like a gas tank here. So we're going to focus on this image of the Gulf of Maine offshore. And I'm always going to have some form of a color bar up here in radiance units. And so what you need to take away from here is two things. One, we have all of these steps. That's how our processing works. Others would proceed differently, but have all the same components somewhere. And that in radiance units, we are mostly in the 50s, sometimes up over the hundreds here, okay? So forget the units, just understand that big number. Okay, that was my remind me to talk about that. All right, so there are a couple of known terms that we can just get out of the way right away. We know the solar constant, that's the irradiance at the very, very receiving the top of the atmosphere. We make the adjustment for the Earth-Sun distance, and we know how to do some kind of geometry. So of course, you need to know where you are, and that's why you navigate your satellites and so forth. Okay, so transmittances, to get to your question. We have a couple of different kinds. We have diffuse transmission of gases, absorbing gases. So this is things like NO2, ozone, oxygen, water vapor. And then you also have transmittance of the actual light from the ground to the top of the atmosphere. And so basically, I'm just pointing out that transmittance comes in different forms, depending on what variable you're talking about. And we consider them both in the direction of the sun and in the satellite as denoted by an S or a V. So you may have already seen these in these classes, but this is just an example of the spectral transmittance for various gases that get in the way in the atmosphere. Here, oxygen and water vapor here. What's overplotted here are some heritage bands on ocean current instruments. And you can see that in certain places they get very strategically placed to avoid contributions by water vapor and oxygen. There's an oxygen and the absorption band here that we intentionally avoid. So start thinking about moving to a hyperspectral universe. We're no longer avoiding these things, which creates a very different kind of problem looking forward, because now we have to account for them. Like if I don't account for these features, you will see them as a residual in your remote sensing reflectances. But that's just for the future. Ozone is one of our bigger problems. It really does have an impact on our retrievals. So and look where it is too. It's in a lot of band regions that you care about. Chlorophyll is calculated right around here. If you're doing some phycopigments, they would be right around here. There's an ozone signal in your way, so you have to correct for this if you care about getting to a biogeochemical property. And then you actually have NO2 in the way as well too. So cool, we know where all these things are, but you can see that they vary with their own concentration. They also vary with their height in the atmosphere, which creates another problem. And so in this case, you can see kind of in kilometers where ozone density as a function of latitude varies, vertically, and that it's actually in a different part of the atmosphere than where you would get, say, NO2. So just a couple of things that we got to deal with here. So how do we do that? Well, this is where our first source of external information, that means external to your ocean color instrument itself, comes in. So we can't proceed without some measure of ozone, like we just talked about. So there are satellites and there are models that actually provide estimates of ozone on global scales. And this is just an example from a satellite called OMI. And we don't really need to take a deep dive into what the math is, but it should look generally familiar. It's a different notation, but it probably should look a lot like what your irradiance profile looks like when you scale it with an exponent. You have a KD in there and you have a Z in there, right? Or your absorption measurement as it's getting attenuated. That's what you're looking at here. This is your attenuation coefficient. And the angles basically represent your depth. So again, same kind of problem as you're measuring light or you're measuring absorption in the ocean. But anyway, what we need from here is an actual measurement of ozone or whatever your gaseous transmission gas is. And then you need some measure of its spectral shape. And those come from lookup tables. So this is external information that we're pre-computing. And like Emmanuel said, all of that has its own uncertainty. This is one way of describing the uncertainty, simply in the form that you can get ozone from different places. We're now using a Goddard or a NASA model for this, but here's an old time series of two different instruments in a climatology. And you can see, while their patterns are generally similar over the course of a year, that their magnitudes shift. And so already now, my choice in what ozone ancillary data source is can influence what my output chlorophyll is away. So just something to keep in mind here. We do our best. I mean, maybe this is something you don't worry about if you trust the agencies. That's great, but understand this is somewhere in the machinery that influences your research. And then, of course, just a fun map of nitrous oxide or NO2. Of course, when you get to more urban areas, this becomes an increasingly big problem. So, if you're near New York City or Philadelphia, this is something that you need to deal with. Unfortunately, these are interesting areas to study because they're near the coast. So now you have something else on top. All right, all this is just to give you a sense of what the patterns look like. So this is diffuse transmission of gas. You can see just it has a little bit of structure in here, but transmission and for this example is still less than, mostly 99%. Same thing for the solar viewing angle here. So don't stress too much about that. Any questions about gases? Luke, did I get enough towards what you were curious about? No. Okay, instrument polarization is something you need to care about. This depends on the instrument that you actually care about. There are some satellite instruments that put depolarizers in their four optics, so it scrambles all the light and you don't have to deal with polarization. There are others like Modus that have a polarization sensitivity that wasn't well characterized when it was launched. And you can see the effect of it in here. It's not much, but it's just one of those other little contributions. So this gets into how you might need to be very careful in the laboratory ahead of time with your instruments, characterizing all of this. It's not a super sexy thing to think about, but it is a problem. And there's been a lot of work. And again, this is just for your reference in how to correct for such things. But that's not a super fun one. So let's just move on. All right, foam and white cats. And here, if Robert wants to chime in, because you've done some work in foam and white caps, please do so. There. All right, so if we talk about it later, I'll just go real quick now. It's an empirical relationship. So here's one of those things where data you collect might be used. Wind speed, so new ancillary data source. Our satellites don't measure wind speed, our ocean color satellites don't. So now we need a measure of wind speed to come in. Usually it comes from another satellite or a model. And then this is the fraction of weight cap for two different kinds of seas. And you can see what we're just using is a linear relationship to go from wind speed into some fraction of weight cap. And then we really start waving our arms. We have to convert that fraction somehow into a reflectance unit. What we used to do long ago was take a paper from 1984, which said that the albedo as a function of fraction of weight cap was somewhere between 11 and 33%. So we picked 22 because it's right in the middle. Yeah. And from that, now we come up with some estimate of the fraction of reflectance that results from white caps. So this is really kind of an unresolved problem that is based on field data. Just to give you a sense, however, here of the impact of all of this. This is a distribution of wind speed from some global image long ago. And you'll note that for the most part, we're in the 7 range in terms of a mean and a 6 of a median for an average global wind speed. So the correction for the most part is pretty low. The fraction of weight cap is pretty low, which translates into a really kind of tiny number here. But it is substantial when you get to higher wind speeds. You remember from the other day, I mentioned there were flags and masks. We tend to mask out anything that's above 12 at that point. But again, do you remember why? That's really not that big of a deal. What usually accompanies high wind? Clouds, yeah. So you're not seeing those pixels anyway. Okay, there has been some recent work on this. So for your later information, check out Heidi's paper, and Robert will talk about this further. This is the corresponding map of wind speed for the image I chose, and this is the corresponding radiance from foam modulated by transmission to the top of the atmosphere. I bring it up just so you can, you can basically see the geographic pattern. The more wind speed you have, larger this number is going to be. But remember, our first color bar was from like 0 to 50. Yeah, we're looking at a really, really tiny number here. So not a major contributor for this example. Southern Ocean might be a different thing. Okay, Rayleigh scattering. So this is molecular scattering in atmosphere. You have probably seen something like this in your ME labs already. Yeah, okay. Choice, yeah, all right. So let's not belabor that other than to say that we're looking at this here with a scattering phase function that's symmetrical. This is again for your record for computational efficiency. We make an expansion here of the equation and create these lookup tables, but the lookup tables are generally global averages. Okay. If we didn't do it this way, the lookup, there's even choices you have to make and how big your lookup tables get. The point I want you to take away is that it's a singular lookup table, but Rayleigh varies as a function of pressure. Why is that? Why would pressure influence a really radiance. Exactly. Yep. So you need to have some metric of molecules, basically density here. So we calculate these tables. Of course, there are their own challenges in these tables. Some don't actually take into account the curvature of the Earth. Some usually have a flat surface and so forth. They're generally accurate, but there are small variations. We do consider polarization here. And the lookup tables are navigated by solar and satellite viewing geometries, wind speed, which is a proxy for surface roughness. So again, we need wind for the second time. And then atmospheric pressure, which as Terrence mentioned, is proportional to the number of gas molecules. And so it adjusts the Rayleigh optical thickness. And then here's just an example of what you might get from a field of atmospheric pressure at any given time. So we make these calculations through lookup tables. And why you care about this is, again, looking at a fraction of the total signal, this Rayleigh radiance is a substantial amount of the total signal that you have here. That's a good thing in many ways, and it can be a bad thing if you do it poorly. This is just showing that another way. If I just start taking off all of the things that we've talked about, we have our original image. If we subtract all of our Rayleigh signal, which I'll show you goes from roughly 30 to 60 units here, this less this gives you an image that looks like that. At this point, all I'm going to do is transfer my color bar now to 0 to 20. This should start looking familiar, right? This is starting to look like the maps that you would normally see. But I've had to rescale from 0 to 50 to 0 to 20. So this gas tank is starting to get lower, lower, lower in terms of total signal available for the work you're doing. All right. Another monologue. How are we doing? Doing okay? Okay, another fun one, sun glint. Ocean color can't be seen through sun glint. Duh, you've been on an airplane, you look out the window, you can't see the color of the ocean if you're looking into the sun. You already saw a picture somewhat like this. This is how it manifests in like a true color or an RGB image at the top of the atmosphere. You can see the signal here. So I mentioned the other day that we make some choices in instrument design related to tilting versus non-tilting. So if we can't see through sun glint, what does that actually mean? For an instrument here that could either be descending or ascending, it doesn't matter, but looks straight down. So it looks at nadir. And it's still looking side to side, it's looking at nadir. For this particular example slot, anything that is in this dark blue range here is effectively unusable. If you were to tilt, so if I'm heading north and the sun is right here and I'm tilting away from myself, say 20 degrees, go through a tilt, and then so I'm always looking away from the sun, you can collapse that to this. In real data, it will look like that. So this is the same day, same scene with Sirius and Modus. They have different orbits, which is why one is going in this direction, one is going in that direction. But you can see Modus, which is a nadir tilting instrument, loses all of this information. And of course, this varies with sun position, so it varies with season. Whereas CWIFT by tilting collapses that down into a much smaller ellipse. Of course, you do lose credibility in some data while you're actually tilting, because your instrument's moving and it's sometimes hard to navigate that well, figuratively and literally. All right, so anyway, that is why we make certain choices. This is the impact of glint. If you left this alone, you lose a lot of information. So has Moby come up at all in any conversation or, during the, where's Moby located? Where's sunlit? And where's it mostly? Yeah. So we put our calibration source right in the middle of the sunlit pattern. Yeah. All right, sun glint. Again, we just do a transformation of the equation, don't sweat it. What we're really looking for here is to translate some metric of what sun glint could be observed as into a radiance unit. This is a paper that goes way, way back that talks about a normalized glint radiance, no atmosphere, solar constants equal to 1. Don't sweat the details here. That is a function of sensor viewing angle and wind speed. So yet again, we need a credible metric of wind speed. But we're using a very, very, very old paper on this. So again, there is one problem that we have here, is the calculation itself requires information we don't already have. So we put in an iteration here. Don't worry about any of this in context of what we're talking about today. Just understand that we can, from wind speed, get to some normalized value of radiance that is a function of glint based on wind and viewing angle. We do need to have a transmittance from that to the top of the atmosphere. Knowing that transmittance requires some knowledge of what the atmosphere is, because that signal can get attenuated by all the aerosols. Have we determined what the aerosols are yet? We have not, so we don't know that. So we take some guesses and iterate to overcome that. That's really all of that does. Again, depending on where you are, it doesn't have to be a huge signal. And up here, we're far enough north. We're, what are we, somewhere around 42 degrees north here and 45 up here where we are. So this is the glint pattern in the image that we have here. You will notice that the contribution isn't super high, but it does as you go south. And generally, this is one of those thresholds that we talked about the other day too. We have to make some choices about what is reasonable glint we can correct for and don't care about, what is too much. So now we're making a choice. In this case, another number was picked. And the impact to you in all of this is that based on that number, if it exceeds it, if it's 0.005000001, that pixel's dead to you. It's not there. But if it's 0.04999, it's considered usable. So there's some black magic in here as well. Okay. Yeah. So we've done everything else perfectly. And now we have to get into our greatest unknown, which is what is the aerosol signal? And how does that aerosol signal interact with air molecules? Again, we have to go back to lookup tables here. That's not entirely true. Other algorithms will express aerosols, which are smoothly varying, as you see, as an exponential or a power law or something like that. But nevertheless, however you do it, you're making some assumption about aerosol properties. And so we characterize them by their particle size distribution and their complex index of refraction. I'm assuming some of this is familiar because you're doing the same thing in your labs in the ocean. This is just another fluid. It's just a fluid you touch in a different way and you can't see. So if you have a particle size distribution and you know your complex index of refraction, you make some assumptions about these being spherical particles. You just do me theory, which you've already, have you done the me lab yet? If not, you will. Yeah, okay. So come out with a scattering phase function, a single scattering albedo, an extinction coefficient, and then you can relate what we really care about, which is aerosol optical thickness, to that extinction coefficient. And then you generate a series of different tables for combinations of particle size distributions and indices of refractions. And those lookup tables are defined by basically the values that you calculate from me theory. So scattering phase function, single scattering albedo, and the conversion of extinction coefficients into an optical thickness. There are a couple of other variables now, and then they become navigated using solar and sensor geometries. The PSD gets a little bit more complicated. Generally speaking, we represent them with two long normal distributions, one distribution of fine particles, another from coarse particles. So you would basically have different mixtures of these represented in your lookup tables. And they are also modulated by relative humidity. Why? That, yep. And their size is, to do what, they're more moisture in the air and they get bigger or smaller. So you, okay, satellite measure relative humidity. No, so yeah, I now have to bring in a metric of relative humidity as well. You know. So we do it with ancillary data here. Okay, so 80 aerosol lookup tables. We use AirNet, which is a series of robots that are on buildings and towers all over the world, and they make atmospheric measurements. Those 80 lookup tables are broken down into 10 PSDs and 8 relative humidities. So that's how you get to 80. So let's pause for a moment in our multispectral universe here. If we're talking about Modus, we're talking about maybe 9 wavelengths, right? So you have lookup table, 80 lookup tables that basically have 9 wavelengths to do all of this in here. We have 200 something wavelengths for OCI. So does that seem like a tenable problem? So now you'd have to carry around all of these lookup tables. You'd have to navigate all of these lookup tables. You have to interpolate across lookup tables. You can do this with 8 or 9 wavelengths. If I have 200 wavelengths, that's going to slow everything down, right? So they've just jumping ahead a little, and maybe this is of interest as you go through your career. Started thinking about how to use the kinds of things Patrick was talking about 2 days ago, machine learning, principal component analyses, ways to calculate these lookup tables and then simplify them without losing accuracy so that they can be navigated much faster and with much more efficiency. Again, just a quick aside, but everybody's so excited about hyperspectral and there's so much we don't know how to do with it yet. From little stuff, you know, even just like, how do we do an atmospheric correction? Well, we know how to do that, but you mechanically suddenly have problems because of the data volume. So it's a new world. Okay, the lookup tables. Oh yeah, sorry.
If you're measuring hyperspectral speed, then you estimate air selectiveness based on the absorption of these. Like it's very long. Yeah. So you have more information about aerosols from the satellite. Yeah, all the ones. Yeah, different event range. Yeah, is that also maybe?
So one of the holy grails in all of this is saying, hey, maybe we know more than we believe. I think people realize that. What, in terms of the operational use of that, we'll talk about it later. But there's a lot more information than we have for that. So there are new approaches that, yeah, like I'm going to show you a human approach from your people and other staff creating solutions that use far more spectrum than complicated by what is modulated or single in ways that are created that we don't have to worry about. You remember? If all that actually see looking feature that's so that is not you have one spectral information, now you have all this extra stuff in the way that you have to do really, really well. So you will leave a residual signal in that then with compromise all this new information you're using for something like this.
Do those things at the area of this house?
I mean, some might be solved, like, you know, I know too, for example, giving some geographic regions and for the parent solid, but understanding about what's the area that's people have to relate to those conditions, things like that. Which is probably like an oversimplification. If others were here, my atmospheric colleagues in the lab might wonderfully provide a 30-minute soapbox on the details of that. I'm not sure. Okay. Oh yeah.
We know how they're doing the atmospheric correction for Prisma, solving for all of this hyperspectral.
For Prisma, I actually am not sure. I know that ISOFIT is a popular hyperspectral atmospheric correction that was based on like ATREM and some other type models, but so there is work towards this. And this would translate, I think, better into polymer, which, you know, is using a smooth fitting for everything, but I don't actually know what is being used there. So I'm sorry, I will look it up for you. All right, just two terminologies here that are only important because it defines how you select your aerosol. You have angstrom exponent. The angstrom exponent is basically defined like this. You take a ratio of two aerosol optical thicknesses, and it's effectively just the slope of that ratio. And it's modulated by the size of the particles, which is important. And then a fancy term, epsilon here, is really just the ratio of two bands in the near infrared. So in this case, we're using 748 and 869 for Modis. The reason you care about all of this is the way we describe our lookup tables comes in the form, we've seen how you describe, and the way we describe our aerosol models comes in the form of the angstrom coefficient and the epsilon coefficient. So this is a graphical version of epsilon. So think of it as the slope of any one of these lines. So you have the shorter band here and the longer band here, which is just that ratio. And the slope of the line also varies with, you know, particle size. So you have some competing information here as well. But again, do we know these values yet? We're really just setting up the framework and the equations. We still don't know what these are. Okay, so this comes into something that was incredibly clever in the 80s called a black pixel assumption. So as you've seen in water like this, probably breaks down, but in open ocean water, can you make the assumption that your near infrared ocean is black? Is there any light coming out of, any red light coming out of the ocean way offshore? There really isn't. So you make that kind of assumption. And so that way you can assume that by canceling out this term, you've added a check over LW for these two wavelengths because you zeroed it out, which means anything that is left comes only from the aerosol. Does that make sense? Okay, so that's pretty much what I just said, which is we zeroed it out. In this case, just to simplify our terminology, I'm going to combine that term. It is a rabbit hole. It's wonderful, but it basically deals with whether you treat the solution space as single scattering or multi-scattering. Assumptions were made long ago. New assumptions have replaced those. It is a series of another series of papers. That's too much for today. But effectively what you are doing is saying, I have a measurement that I can now believe of water leaving reflectance, of aerosol reflectance in the near infrared. Because basically I've zeroed that term. So all that's left in our calculations are these terms. All right. So now I can calculate an epsilon in those bands, right? Which is basically just taking the ratio of two things now I think I know. So you pick the 8 aerosol tables that match your measurement of a relative humidity, and then you calculate the epsilon for each of those 10 tables, which you can do just by navigating the lookup tables, and you might get a series of non-dimensional epsilons from those tables that looks like this. Now you have a measurement here, you have a measurement here. So basically your solution space in terms of your actual observed epsilon is somewhere in there. So you end up doing another iteration, but the point is that if I can narrow down my series of lookup tables to this, and I can calculate an epsilon from my satellite by making that black pixel assumption, I just basically find where I fit into the solution space. And from that, I basically pick an aerosol model. I do an iteration, so I basically narrowed it down to the two that my measurement falls in between. If that's true, then I can, so let's say, for example, I fell here, then I can just tell you, oh, good, my epsilon space is going to be like that, and I can extrapolate it into the visible. So a lot of words just to say that. But basically what it's saying is that if I can make this assumption, I know something about the near infrared, I can navigate these lookup tables and I can make an inference about what's happening in the visible. This one's a lot. It's very messy and it's been updated and then revisited. But from a general concept of what we're trying to do here, what should we go back to? Or is it good enough? Just like there's a dark art to coming up with aerosol selection. Why would anybody do this? I should switch fields. They don't do the atmosphere anymore. All right, well, let's just say it's good enough and you can ask me later if you care about it. This is where the fun comes in. Is this assumption valid? So here's remote sensing reflectances calculated in the Sargasso Sea near Bermuda. That assumption is actually pretty good here. If you zoom in, that's a really negligible signal for the most part in the grand scheme of things. So my black pixel assumption is probably okay, which is why honestly our offshore radiances are really, really very good. If I go to Chesapeake Bay and I make the same measurements, you might get a spectrum that looks like this. Imagine it's familiar, but it's not what you see offshore. But if you zoom in, suddenly that signal is no longer negligible. And so your assumption immediately breaks down. And if you ignore that, and you just say, my assumption works about that part of the ocean being black, so I can do my atmospheric correction, and I just don't even try to make a correction. What typically happens in these bodies of water is that you select the wrong aerosol and you overcorrect because you're saying that signal is something that it's not. And so this is just for the bottom half of Chesapeake Bay, something we did long ago. I just wanted to show you the distributions of remote sensing reflectances. If you make no correction to this, you just assume that thing is valid. And you can see you're really getting into negative water leaving radiances in the blue, which influences your chlorophyll retrieval and everything else that goes on. This is a time series, monthly time series of it. You know, on average, you just have negative radiances. So not happy data at all. And so this is an old slide, but there has been a remarkable amount of work in trying to address this. Like, how do we modulate this assumption so that it is applicable to places where it is going to fail, like Hartsville Sound? So one of the neat ideas was just simply assign aerosols or assign water leaving contribution. Like you have, so this is something you might consider if you're doing your atmospheric correction here. You have measured, you might not have an aerosol measurement, but you have a water leaving measurement. So you can take something like CDAS, like I showed you, and physically override this whole process with real data. If you're using an instrument that has them, you can say these red bands are inadequate, but if I go into shortwave infrared, it's got to be black there because it's farther, they're longer bands. So use them instead. What might be a problem with that? So those aerosol tables, you're already extrapolating from the red into the blue, right? So you're going from like 700 nanometers to 400 nanometers. Most of these bands are like 2200 nanometers. So now you're doing a very, very long extrapolation, which could get lumpy. Use a couple of ocean atmospheres. You can do that. Those are those more computationally expensive solutions I told you about. And then you get to where we really landed today, which is use a biooptical model. What goes into biooptical models? Empiricism and all the field data you collect. So now suddenly the data you've collected and will submit to CBES might be used in a biooptical model. Thing is those biooptical models for the most part work. So this is the same thing where we did the correction and you can see that we've greatly improved our retrievals. This will not impress you. This is a really, really simple optical model. We start by making an assumption that the value in the red at 670 measured by the satellite is good. We then model absorption. Modeling absorption requires the estimate of water, plus, of course, the estimate of everything else in the water. We modulate this by a first guess at chlorophyll. Chlorophyll is a band ratio of blue and green, which we don't know, so it's kind of a crappy guess. The good news is that absorption by water is so big here that even with large chlorophyll values, it's just a tiny modulation. We then basically just estimate backscattering using an inversion of this. So if we know remote sensing reflectance at 670 and we know absorption at 670, we can come up with backscattering at 670. But we don't want to correct at 670. We want to correct in the near infrared. So now we have to make a guess at a backscattering spectrum slope. So we use another model to come up with that from QAA. This is field data. I mean, have you played around yet with your data enough to actually see how a backscattering spectral slope varies with band ratios? It's really, really nice. So anyway, this is just sobering. You work some other black magic and you effectively come up with backscattering at 675, which then you plug back into a Fourier model. You just assume water is dominating absorption because it's almost 3 inverse meters at that time. And you can come up with a modeled value of a near infrared reflectance. And then you just iterate until that value stabilizes just by reseeding this whole iteration. So I'm gonna leave this for your reference. The point being is that there is an empirical ocean color correction embedded into atmospheric correction to correct your aerosols. So it's a very, very circular process here too. Yeah.
Is the water corrected?
Nope.
The one starting.
Backscattering is, but water is not.
Was that for any 107?
It's currently not correct with temperature.
Exactly.
It's not backscattering, it's the water is not. So.
Easy things.
Reach into the choir. Just a sense of a global map of what the correction looks like. So, like I said, for most open ocean waters, you do no correction. That's all of this gray area. The assumption is totally valid. It is fully applied when chlorophyll reaches a certain level. So that's really in the deep coastline. And then there's a weighted application somewhere in the middle. So devil's in the details. Just go back to the paper or read Kurt's then. Again, point being, data you collect gets used for all of this, which makes it scary. Okay, so that's basically aerosol selection. But what I meant, what I tried to do is make it more of a historical perspective. There's been a ton of work on this since then. How we've done this historically is not necessarily how we're going to do it going forward. Robert will touch on a couple of these. This is the multi-band version that we were talking about just a few minutes ago, where you use more spectral information. There's a spectral matching approach called Polymer that you're already familiar with. That does some really, it makes different kinds of assumptions. Some are better, some are worse. But there are places it works far better than this approach. And then really, again, the holy grail is you do this as a coupled system at home. All right, so one problem we haven't touched on that maybe Robert will is everything I've talked about so far does not consider absorbing aerosols. And so very interesting places have absorbing aerosols, brown carbon, black carbon, all absorbing aerosols. So the question, and Kurt posed these, why not use a wavelength in the ultraviolet, which could distinguish between absorbing and non-absorbing aerosols? Well, one problem is the water isn't actually black there. So why not go even farther into the ultraviolet where the ocean is again black? There's no sunlight there. So this is one of those promises of hyperspectral, like we're going to do way better with this because we won't constrain our solution space to the near infrared. We'll go into the ultraviolet where you have a fighting chance of seeing whether your aerosol is absorbing or non-absorbing, but there are a bunch of physical challenges in the way. Solvable, maybe through some machine learning or other things, but imperfect right now. Boy, you need a break. Okay, so anyway, here is back to the gas tank. This is where we were. This is the aerosol signal that we would retrieve for this value. Again, the color bars are exactly the same. Over here, we're looking at 10-ish, and then you're taking another huge chunk of that out. So if you subtract your aerosols from where we left off, you ultimately end up down to an almost final water leaving radiance. That would look like this, which should be familiar. We started with 150 being here. We are now down to 6. So we've done a lot to get to this point. Okay, very quickly on some of the other little rabbit holes, and then we'll wrap this up. This comes into an instrument design flaw, not flaw, feature. If you were to look at the spectral response, and I know this is falling back into when you were first talking about instruments here, like never trust the manufacturer kind of thing, like you don't know what your instrument is doing until you take care of it yourself. If you look at a linear axis, these are Modus Aqua bands, their spectral responses look very well separated. If you put it into log space, there's a lot of overlap in all of these, and it might not look like much, but if you just take a peek at this purple line, 412, there is a 1% contribution from green light that is leaking into the filter at 412. So your 412 signal, if you do nothing, is imperfect because it is not just blue light. There's light from somewhere else coming into it. And you want to adjust for that. And without belaboring the details, here we go. We created correction for this. The correction factor is determined as a function of chlorophyll. So digest all of this for a second. You now have radiances that you need to correct again. So you calculate chlorophyll to go back and correct your radiances. The factor can be somewhat benign. In this case, you're talking about 2%. In other places, it can be up to 8 or 9%. CWIS had a really, really bad leak in one of its filters that had to be adjusted for. So it's different for each band of each sensor, and we use a Clearwater reflectance model to adjust for it. There's one other reason that we do this. It's not your problem anymore, but it was when you only had multi-band radiometers. So back in the day, there were 7-channel radiometers like the HyperPro. They weren't hyperspectral. They were only measuring 7 wavelengths. The 7 wavelengths usually matched the satellite. Those had band passes that are different than what the satellite actually had. So we would use a correction like this to get them to overlap based on chlorophyll. Fortunately, that is not something that is necessarily applicable when both are hyperspectral, but there is a nuance here when you are doing your matchups. So right now, this correction is enabled by default. Okay. So if you were to go and download level 2 Landsat data from us or Aqua data from us, you have this band pass adjustment being made. So you've taken the full spectral response of an individual wavelength and made it into this little 10-nanometer box. When you're using a multispectral radiometer, that's great. If you're using what you have access to, your hyperspectral radiometer, then you need to either do 2 things to get back to apples to apples. You either need to take your hyperspectral radiometry and apply some kind of filter around it to mimic what we've corrected to, or you need to reprocess and disable that adjustment. And then you need to treat your hyperspectral data with the spectral response function that matches what the satellite is. And those are available online, but you have some choices that you need to make when you're taking your data and making it look like the satellite data or vice versa. So it's a little bit of extra work. Okay, and then last we have something we touched on quickly, which is the bidirectional reflectance correction. This is another fun one. In a cartoon sense, this is what we mean. We talked about this in one of the data processing labs on Tuesday, but not either. This is an attempt to once again normalize a measurement made one way with a measurement made another way. In this case, it's basically based on time. So you make an in situ measurement, the sun might be in the sky in one place, and you might have some kind of feature in the upper ocean in one place. But with time passing, of course, unless you're exactly measuring at the exact same time, the time of your satellite measurement will not necessarily be at the same time of the field measurement. The sun will be somewhere else, and your water mass may have changed. So we create a normalization to adjust for this. Now you can do overpass predictors. You all might be smart enough to know exactly when to go out. But if you're doing a satellite to satellite comparison, you're just at the whim of whenever the satellites collect data. So to do an apples to apples of the two satellite measurements, you need to perform this correction to normalize to a common condition. Said that already. We do this normalization. Here are things to consider. It's the path length through the atmosphere, transmission of light, and angular features of the Bowdoin scattering function. What's operational now is different than what you talked about in your hyper CP class. I think you're evolving into the Lee and others 2010 version of this, right? The hyper CP is doing the Lee 2010 version of the area that is trying to get to that.
Right now, which is the
Okay, so it's the same one as there. So it's a nice paper, it's a series of papers, it's a long read. Basically, there's just a series of lookup tables. Those lookup tables are based on chlorophyll and geometry. Geometry, we know exactly. Again, yet another estimate of chlorophyll going in to correct your radiances. And you can see what the difference is. You know, it makes some difference in blue water and much more difference in green water. Give you a sense of the correction factor, just showing it another way. Very little offshore difference here, but as you get near shore, this correction can reach up to 20%, which is a lot. And again, seeded by chlorophyll. But if you do all of that, now remember, we're doing all of this for how many tens of millions of pixels every 2 days? There's a lot of stuff going on in there. Okay, everybody's tired and needs a break. I had another Menti slide on where you thought the biggest sources of uncertainties are, but let's just voice that over. So all these moving parts, what are you afraid of in terms of uncertainties? In everything is a totally legitimate answer. Well, let's start with this. Is this system linear? Were there iterations? Were there lookup tables? Okay. Does every ancillary data source come packaged with its own uncertainty? So if your pressure is off, or your ozone's off, or your lookup tables are off, you know. So propagating uncertainty from all of these sources into a pixel by pixel calculation of RS uncertainty. Been a big job that's only recently even been trying to be calculated. You know what? Think about it. Tomorrow you're gonna have an uncertainties lecture. If you want to do some homework, there's a paper on it that does some attempt to get to pixel level uncertainty for MODIS. You can see that it's got some moving parts. All right, so this is a scorecard. This is one of the, we've walked through the mechanics, you're all through the meters now. Just showing you the laundry list of ancillary data required. We never even touched on the ice or sea surface temperature for biological algorithms. In the past, for all of these, we got the data from NOAA and from satellite data. Now we're bringing it in from a model being run by NASA, but it's a lot. You need a lot of external information. You have all your lookup tables and coefficients for all of these parameters. And then of course you have all the empiricism in the world. But at the end of the day, you can build things that look like this. You've seen this, I hope. This, to me, is more important than the moon landing. This is NASA's crowning achievement. It is 20 years of watching our planet breathe collapsed into 2.5 minutes. And you can watch the seasons change. You can watch the forests on land and the ocean get bigger and smaller. If you know what you're looking for, you can get scared that all these deserts in the ocean are getting bigger and bigger. Anyway, break time, no? So question, just good. I'm here for another couple of days. If you have any questions, Robert's here. He is even better at this stuff. My next 2 lectures will be way better than this. One is a 5-minute one that gets you excited for tonight, but maybe we'll save that till after lunch. If there's some enthusiasm.
The fact that there's
Well, so we're going to do this assumption that the next week. So that's region A, region B, region C, they had all the different, there's some combination of what's in the different. So, that region is outside, just see the ground profile, right side, or energy, and through that, you know. But that said, again, if we become a savvy with the process, so you can hold, you can run, there's something you can plug in, you can go over that. Then just say, I don't believe any of this, I have to read that, but it's on, that's no, what kind of so this. Now we're going to see this, and then people read it, they just accept what's coming out. Whereas there is more and more information that could be used as inputs to reduce some of the assumptions. So I would highly advise storing it versus letting it run through. This was the high level. Sweet Kurt's
So I just have a question about like, uncertainties in terms of water beauty gradients that we had recalled that, you know, for case, the goal of 5%. I mean, something that we talked in the class about is, you know, how big should our error bars be and is it achievable? And then I think about, I see all these different correction factors we need to make with just atmospheric correction, and I don't know, like the fact that our signal is so small, and it's just hard for me to think that we can reach that 5% uncertainty benchmark, which maybe 460 nanometers per RS for LW. Okay. So, but you're confident that we can get there, right? So, what makes you sleep at night? Yeah.
So there are two things that, at least looking forward. The first is, since you have a sense that it needs to be 5% of the advance. You're going to do up the atmosphere, it has to be a half. For technical condition, right? So a half of the percent is going to be and then you go to a bunch of unbelievably brilliant engineers like Scott, they have infinite number of students, and it's like how they design building tasks in the lab. Of course, that's the changing time. More common things beyond trusting the instruments. Very good at temporal calibration students, see regulation. And then you have something like here is calibration, which is final adjustments that really release the pressure. It has to be done well, which is why I have these very complicated, but very thoughtful programs to make like the message feel. But as something like this calibration series, there is an adjustment, but I think that has to be fairly large. Because we're going in orbit, the atmosphere is in a way, and so general biases that might introduce itself. If this is for that, you can't look for that. The atmospheric correction procedure and resolve. So a little about the absolute matter is going to be now because it's the factor. I mean, this is what I try to think.
Yeah. I hear his calibration box to super stats.
Yeah, would be either, no matter which you know about that role and then absolute. Yeah, absolutely. In fact, missions like viewers are not intended to be that's that they have the other one. So this hypernet, well, hopefully a hypernet will show up. Sweet. So, but that is definitely gonna be useful. It's pretty, it's, I don't want to keep you from snacking and talking.
No, I think I'll.